Right, class, let's continue our talk of applications of definite integrals. So 5.4, we learned what a definite integral was, and we talked about the fact that it helps us find the accumulated accumulated gain value from point A to point B. And so what we're going to do in the next sections is just explore more of the applications of definite integrals. So the average value of a function is just that, another application of definite integrals. Okay, so what does that mean, finding the average value of a function? Now, if you could think about a function, a quantity, I should say, I'm just going to write this down. A quantity takes infinitely many values between 2 points, right? So if I were to think about what's the average value of this function from here to here, right? That's the same graph there. Now, what does it mean to find an average? To find an average all along has always been the same. To find the average between some values meant always to do what? What do we do to find the average between some values? Add them up. This number and this number and this number, fine. Add up all the numbers and then what? Divide by the number of values, right? By how many they are. So let's say if I want to find the average between 1, 3, -2, and 9, what do? I add them all up and divide by, I'm averaging 4 values. Whatever this might give you, I don't even know, I just made something up. 4, 13, 11 over 4, whatever. That's the average. 3.75. Yes, that's the average between these values, right? Now, the thing is, if you have infinitely many values, what are you going to do? First of all, I can't even add them up, right? There's infinitely many points. Yes, this is the value. At A, the function takes this value here. A little bit over, it takes this value. A little bit over, it takes these values. So to find the average value of a function means to add up what? All the possible y coordinates, yes, of these points. That's the value of the function. Add up all these y coordinates, these heights, yes, and then divide by what? By how many you've added up. Well, if there's some infinitely many, first of all, I couldn't even add them. Second of all, how do I divide by infinity, right? That's just not going to make sense. So, clearly, that's not the way. Same as what? It wasn't the way to find an instantaneous rate of change in a function with just 1 point. Yes, so what did we do? We approximated and we said, hey, if you get close enough, your approximation is just pretty much the value exactly. Yes. The same thing in 5.4, we learned, how do I find the area under the curve? Well, I can't sit and add these infinitely many rectangles, right? So the more I have, the better the approximation. So we found a way, right? Again, approximating with a few and letting that n get close to infinity, finding that limit. And it turns out that it's just the super easy fact to find. Yes, just finding the definite integral between two values. Now, to figure out the formulas right here, the ideas right here, I'm going to take you back to something that we would know. So let's say that you have a function that is constant. What do I mean by a function that is constant? Well, the height is the same, yes? So if the height is the same, then clearly the average value is this value, right? There's no secret that it doesn't go up and down to find an average. If it's all 5, the average of a bunch of 5s is just 5. So, however, what I'm trying to do is get back to what we've learned in the last section. Now, if you look at the area under this curve, what does this area form? Obviously a rectangle, yes? Okay. Now, what's the area of a rectangle? Is the length times the width. Okay. If you look at this rectangle, what's the length of it? It's anything from here to here. Yes, so I'm actually going to say, let's say that didn't have to go from 0 to something. It could just go from any random A and B. So I'm just going to keep it as some randoms A and B's. So the width of this, the length of this rectangle is the difference from what? From B minus A. So if you start at a 0 and go to a 5, then that width is 5 units. If you start at a 3 and you go to an 8, that's still 5 units, right? So whatever it is, the difference between them. What's the width of this rectangle? Well, the width of this rectangle is pretty much the height, if you want to look at it. What's the height of this rectangle? The height of this rectangle is really the function value, right? This constant function value, which for us is the same, right? For this picture specifically. So if I wanted to solve for f of x, then what would f of x equal to? It would equal to the area divided by the length. So the area divided by this b minus a. And now I squished myself all the way in here, so I'm just going to go up above. The f of x for this specific question or problem, right, where it's constant, makes sense to say that it's 1 over b minus a times the area under the curve, yes? Okay, it's simply the area divided by the length, right? You have two numbers multiplied to this, then one of them is this number divided by the other. It makes sense, yes? Now, it turns out that that's the same even for a function who doesn't stay constant. Why? All we have to do is, well, if this should be the average value, right, of all these points, then what could we say? That the area under this rectangle is going to be the same as the area under the actual function itself. Yes, that's its average. Take a little, put a little, yes. So it only makes sense to say that to extend this rule to the rest of it, that what? The average value of this function, or this height that we call it here, in this picture it's called the height, is simply what? The area under the curve divided by the width of the interval. I'm sorry, the length, fine, of the interval, or the width of it. It doesn't matter which one's the length and which one's the width. So it's going to be 1 over b minus a times the area, just as below. But what's the area under the curve? We learned from the last section that the area under the curve is nothing but the definite integral, right? That was our definition. If you want to find the area under a curve f of x, all you have to do is find the definite integral. So that's where this picture comes from in between. Kind of like to see here, what you're doing is you take the f of b minus f of a, right? So it's going to be this difference divided by the width of the interval. That gives you the average value in this function. Okay, so there's that. Actually, that's the antiderivatives value, not the function itself. So let's not go there. But again, this was your area. And this is the area divided by the width of the interval. Okay, all right. So I didn't make more notes for this. Simply because I'm just going to write it down. Sometimes it's easiest to just evaluate instead of writing too much. So I'm just going to write the problem down. I'm just going to say this. What are we doing in this section? Finding the average value of some function. Let's take the function to be f of x is x to the negative 1. Okay. From x equals to 1 to x equals to 5. Okay, so that simply means what? If you were to plug in all the values into this function between 1 and 5, so what does that mean? 1 1.0001, 1.0001, and then you could be stuck right there with 0.0001s and 0.0002s until slowly you make your way to what? 4.8, 4.9, 4.999, 4.99736, all the way to 5. Now those are infinitely many values, yes? I'm going to draw a picture for you as well. What does the x to the negative 1 function look like? The x to the negative 1, I wrote it this way for you, but that's really nothing else but the 1 over x function, the reciprocal function. So if you remember what the reciprocal function looks like, it's getting closer and closer, by the way, should dip down. And then it looks the same on the negative side. I'm not really bothering with the negative side because it said to find the average value from what to what? From 1 to 5. So really f of 1, if you plug in a 1, you're going to get a 1. That's exactly what I was doing here. I was plugging 1, 1, 2 at 2, I'm getting at a half I'm getting at 2, so those are those points. So I want to find the average value between here and all the way down here. Okay, I'm not finding the area under the curve. I want to find between these two values. So again, what are my two values, by the way? F of 1 is 1. F of 5 is 1/5, yes, which is 0.2. So the average value, as I see it, definitely has to be something between 1 and 0.2. And it's not going to be halfway, by the way. Halfway between 1 and 0.2. Add them up, you get 1.2 divided by 2 is 0.6. So the average value won't be 0.6. Why? Because as you see, it goes down faster and then it kind of lingers down here, slower. So there's definitely more values closer to 0.2 than they are to 1. Okay, so now how are we going to find it? The formula is simple. The formula simply says the average value, and we can just write f average, yes, is going to equal to what? The area under the curve from 1 to 5. That's the area under it. What do I have to do? Divide it by the length of this interval, right? So divided by 4, which is the same thing as multiplying by 1/4. Yes, so that's where this comes from, right? Dividing by b minus a. All right, so what's the integral of this? Now, what's the derivative of an x to the negative 1? If you remember, that's the only one. There's the exception to the power rule, because when you add 1 to it, you get x to the 0 over 0, so that doesn't work. But in 5.2, we've learned the antiderivative of x to the negative 1, or to 1 over x, is simply ln of x. And then we're going to find that, the absolute value, between 1 and 5. So that's 1/4 times ln of 5 minus ln of 1. Okay? And then put that in your calculator. And I'm going to put in my calculator, and it's just going to be, again, that's a 0. ln of 5 divided by 4, the calculator says about 0.40. Okay, we're fine, 0.4. So as I said, the actual average between the beginning and the end, if you were to go straight down, right, no dipping, then the actual average value will be 0.6. But as I said, it's more on the lower side because there's more points that are on the lower side, yes, than on the higher side. So I hope that makes sense. Okay. Without any pictures, just practicing on the formula, let's find the average value of this function. Again, it would be a good idea to have a highlighter and look and read the instructions carefully. We're finding definite and indefinite integrals, derivatives, and so on for several reasons. You need to read the instructions of the problem carefully to know exactly what you are being asked for. So this one says to find the average value. Okay, there's a formula for that of this function. Here it is, f of x is x to the 5th minus 16x to the 3rd plus 4x and minus 1 on this interval from 1 to 3. Okay, so there's a formula for the average value of a function. What is that formula? Again, you take the area between 1 and 3, and that's simply the integral of this. And then you do what? You divide it by the width of this interval. So to divide means to multiply by the reciprocal. So rather than writing this whole integral and then over 2, it kind of looks funny. So it's better if we don't look at it as a division, but as a multiplication by some kind of coefficient. So that's 1/2, right? And now let's just go straight up and take the antiderivative of this. So what's the antiderivative of that? It's x to the 6 over 6, right? Minus 16 x to the 4th over 4 plus 4x squared over 2 minus 1x. And remember, when we find definite integrals, we don't have to write the plus constant. Why? Because we're evaluating this anyways, and we subtract it, and we are coming up with those k's would cancel out. So what I have here is 1/2 times, I'm going to plug in these values. First the 3, so 3 to the 6 divided by 6 is something. By the way, I'm going to reduce this